So this talk covers I3S, the Index 3D Scene Layer specification. We've got it up there. It says an open 3D standard because it's actually already out under Creative Commons licensing. It's also going through the OGC process right now. In fact, it's in voting for approval as a community standard. So we're serious. It really is an open standard. With me today is Tam Belena, and Tam is lead software developer for the 3D services team at Esri, and he's been around for a lot longer than me in Esri land. And he is a key go-to guy for me when it comes to anything technical about the 3D scene layers, scene services. Tam is the guy who has to modify the spec up in GitHub, all that kind of stuff. That's right. So if you don't like one of the screenshots up there, let him know. And then also with me is Sean Morris. Sean is our 3D product engineer. He does a lot of the testing on the big scene layers that come in. I'd say between the three of us, we are kind of like the human parsers for all of the bad I3S that comes in now from partners here and there, and the good stuff too. And Sean has also been invaluable in the last couple of years after he moved over to this part of the team. His background is actually as a civil engineer, so Sean actually is a great go-to person as well in terms of like really using our software to accomplish real-world end results. So he's been great. And then I'm Chris. I've been with Esri only 2.5 years, but my first job offer from Esri was back in 1999. So I kind of just avoided I was in orbit for a while before I came down to Earth. I've been in the 3D GIS space for about 10 years. I was at Autodesk for about 7 years. I was hijacked onto a team looking at 3D GIS problems. I became the first technical product manager on that team and then took it over after a little bit. And there are a couple products out there now that resulted from that effort. I'm the 3D product manager across Esri, but the 3D web services stuff is my primary focal point. ArcGIS Earth is probably the second big focal point for me, and then there's a pretty big BIM GIS effort. Actually, I'd say BIM GIS is bigger than ArcGIS Earth now, but the Earth stuff is mostly focused on the defense and IC communities. So we are in 2017 now, and I'll just say that the value prop for 3D and GIS has changed over the last few years. When I started working in 3D GIS, the value prop was a lot around visualization and communicating stuff that people couldn't see or communicating stuff that didn't exist yet. What you used to hear occasionally is people would say, well, but what I really want is for 3D to become this hyper-accurate version of the real world. And what you used to hear back then is, well, that's going to be impossible because the volume of data required to represent the world in higher accuracy than we can do in 2D simply can't be used. And actually what's happened is in the last 2 months, for the first time in my career, I've actually heard customers start to say, I want 3D because it is a higher accuracy view of the real world. So, and one of the things that's happened is that data collection and the ability to consume massive amounts of data have both improved, they've gotten cheaper, and now we're at this point where people actually can start to see the vision of having hyper-accurate versions of cities, even super detailed, accurate versions of environments around cars. And all that is represented in massive amounts of data at different spatial scales that needs to be distributed, transmitted, used. And so we've got this fundamental problem in that 3D content is large, heterogeneous, and needs to be distributed. And it can be distributed in several ways. And for us at Esri, we're not a startup, even though we're kind of like the largest startup that I've ever been at in the way we operate. We aren't just focused on getting 3D content from a single server application to an iOS mobile device, right? So we have to worry about 3D capability across this entire large platform. And what I have been really focused on the last few years in my job is evangelizing how we're bringing 3D to market. And it is cross-platform. We do intend for 3D to be usable on mobile devices, web, desktop, served out of server and online, all that kind of stuff. We do recognize that in the modern era, new types of content, new ways of transmitting information need to be open. Interoperability is an essential part of the future. And then accessible. And what I mean by accessibility, I've always been a user-friendliness kind of person. I started out working with realtors and scientists, which is probably what kind of burned that into me, because realtors, no offense if you are, or your mom is, or your wife is, or husband is a realtor, but they are the worst group to work with to try to put something difficult in front of, because they'll just reject it instantly, because it makes it hard for them to sell a property or a house or whatever. And that's been kind of burned into me, and a big part of our effort here is also making the content and capability that we're exposing easy to get to. And so that's been a huge focus for me as well. Standards have been a big part of the story for Esri, really since the 90s. Shapefile became a de facto standard once people started to crack it. There are numerous others that Esri has been involved with over the years. And standards and open standards have become an integral part of our 3D story. You may or may not have been paying attention, but we actually have native KML capability in ArcGIS Pro and ArcGIS Earth. We have this thing called LURC that's a patented compression algorithm for storing raster content, and that can be imagery or elevation. In fact, our world elevation service is compressed using LURC. So anytime you guys have used a web scene or ArcGIS Pro with the elevation surface, you're actually consuming LURC content. And we then release that patented algorithm out into the public domain so that people can use it. And there are lots of other ways that we've been working with and embracing open standards around 3D. I3S has been this index 3D scene layer spec that we're talking about today has been a key part of the story for us. So I3S is an open specification for 3D content, and it is shared under Creative Commons licensing. The OGC community is currently considering I3S as a standard. I3S is, Tam will tell me it's not a format. It's a set of specifications that describe layer types and profiles for storing content that can be used to store and then stream a variety of types of content. I3S also intrinsically has a REST service specification for calling it, retrieving it, and then along with it also is a packaging specification so that you can actually wrap up I3S as a single file and open it in ArcGIS Earth or ArcGIS Pro locally on a machine, or give that file to a customer and then upload it into ArcGIS Online. When you use maybe context capture or Pix4D, you generate a scene layer package file that you then can use in a variety of ways. That scene layer package file, the structure for defining that, or the spec for that, is part of the I3S spec. In the future, we'll be adding new layers, right? It's a living spec, and we've updated it several times already, and we'll continue doing so. The point cloud specification that came out in the last 6 months is an example, or the point cloud layer type. And then we're definitely open for feedback, and if we get approved to go through into OGC as a community spec, what has been proposed is that version of the spec will actually be under share-alike copyleft licensing. So if you really want to dive in, you can actually go modify the spec and hand out that modified version of the spec as long as you share that back to the community. So we've released something out there, and we're really looking forward to people making improvements, recommending changes, and participating. Okay, so other things that you'll find we talk about around when we talk about I3S. So I3S describes these things called scene layers. They are the content itself. They're layers with attribution, geometry, stylization, and then what you have to use them, right? So one of the key places where we'll often talk about using scene layers is as content within a web scene. A web scene is a container for a bunch of layers that can be viewed, consumed in a browser, in a WebGL viewer that is called very creatively the scene viewer. And when you go up to ArcGIS Online and you you click on scene, you're looking at the scene viewer, and when you add content in it, if you add a scene layer, it's an I3S scene layer. Let's see, the whole goal for the web scenes, scene layers, this whole new extension of 3D from Esri is to be able to give you and your users the ability to reuse content all over the place, locally on a desktop, through the web, behind a firewall, out on the open internet, to be able to extend it and just give you guys the ability to use the content where you need it, when you need it. We have had, we've actually had really great third-party adoption of I3S. The poster child for adoption is this company, Vricon. They are using satellite imagery to cook very large chunks of the world's surface, and by large, I mean like 10,000 square kilometers at a time. They'll generate scene layer packages that can be 100 gigabytes in size, and then you can take one of those scene layer packages and just open it in ArcGIS Earth. They primarily serve the military and IC community, but they're starting to see interest from the AEC and cities and others as well. We've got a lot of other names that are interested in using I3S, and there are other folks like Pix4D. They provide some tech that is in Drone2Map, and Drone2Map can spit out I3S. We have a whole bunch of other partners that we've been talking to, and I think some folks are waiting for us to get final approval in OGC before they say, yes, we're going to go with you guys. I3S has no commercial dependencies, so just to be clear, it really is an open spec. Anybody can access and read the published spec. They can pull apart I3S scene layers without any threat of violating our licensing. They can create layers if they want, according to the spec. And they can even consume I3S layers themselves in their own application. I3S will definitely be improved by having lots more people both consume and create it. So we do hope to see people start to work with it on both directions. All right. So in practice, what we see is that users can create I3S content in Esri and non-Esri apps. So you can use context capture, Pix4D to create I3S content. Is Safe, have they released it yet? Not yet. Okay, Safe is working on it. You can acquire I3S content from vendors. Like some customers are going to an Aerometrics or an AAM, and they're asking them for meshes which can be spit out of Bentley's context capture in I3S. And then you can share and distribute it freely. Partners, you can build your own writers, you can build your own readers, you can sell apps that can read and write with no dependencies on us, and you can contribute to the requirements and change process for I3S. So now I think Tam's going to take it. And
cool.
You got a mic?
No, I got my mic. Yeah.
All right.
Cool. Thanks, Chris. So before delving into I3S, index 3D scene layers, I wanted just to touch upon a little bit about where we have support for I3S within the ArcGIS platform. So there are two aspects of I3S that when we were talking about this streamable, shareable content. First aspect of it within the ArcGIS platform is where can you create I3S content, and where can you actually publish, share, or generate this content and be able to share it. Well, the ArcGIS Enterprise system is the first one that when we created I3S in 2013 or so, when we released ArcGIS Enterprise or ArcGIS Portal at that point was the first application from the ArcGIS platform that was able to generate and share this content. So ArcGIS Enterprise, composed of ArcGIS Server, Portal, and Data Store, is one of the primary application or products within ArcGIS that can allow you share, publish I3S content. Then next up is ArcGIS Online. ArcGIS Online, everybody loves it. You can work with it. ArcGIS Online also has support for I3S or scene layers directly. In fact, in the July release of ArcGIS Online, we now allow you to publish directly to ArcGIS Online. You can upload your features, publish a feature service, and from that feature service, just the same way that you are accustomed to publishing to tiled map service, now you can do scene services directly from features. And this has been a feature that has been requested as far as sharing, publishing I3S from us, and this just came out in the July release of ArcGIS Online. So that covers both the web approach, ArcGIS Enterprise for on-prem cloud that you might have in your organization, and also ArcGIS Online to share with the public at large. Then next up, the desktop application offerings that we've got for desktop that generate I3S content. First one is Drone to Map. Drone to Map is capable of generating scene layer package, as Chris was describing earlier. Scene layer package is this archive that contains the I3S definition, the node structure, and content of an I3S layer. So Drone to Map is one application that allows you to generate a scene layer package, which you can then upload to ArcGIS Online or ArcGIS Enterprise and share it as a service. Continuing that, desktop products, ArcGIS City Engine or Esri City Engine is yet another desktop product that we have that allows you to generate either procedurally modeled data or imported data from 3D models and be able to create a scene layer package directly out of it. And this scene layer package, again, you can share for your users or public at large using ArcGIS Online or ArcGIS Enterprise. And then last but not least, ArcGIS Pro. ArcGIS Pro is the premier desktop application for handling and managing 3D data and 2D and 3D data. And ArcGIS Pro plays this dual role where you can actually generate directly. You can generate content, I3S content directly within the ArcGIS Pro application itself, and or share directly to your ArcGIS portal, your ArcGIS Enterprise instances. So using ArcGIS Pro, you can directly publish to ArcGIS Enterprise or generate a scene layer package that you can later on upload to Enterprise or online and share it as a service. So as far as publishing and sharing or generating content, these are the products from Esri that we offer that allows you to generate I3S layers. As far as consuming it, the web, is it a little bit too loud? Sorry. As far as consuming it from web point of view, the ArcGIS Enterprise, Scene Viewer, ArcGIS Online, and the ArcGIS JavaScript, ArcGIS API for JavaScript all can consume scene layers directly. So the web aspect of it is covered with this product. Desktop, as I mentioned earlier, ArcGIS Pro can generate the content and also can consume content published to directly to ArcGIS Online, or directly even scene layer package generated and published within the ArcGIS Pro application itself. Same with ArcGIS Earth, which is a freely available product that you can consume scene layer package generated with this product I mentioned earlier, or the service directly from your ArcGIS Online or ArcGIS Enterprise instances. And then lastly, scene layers or I3S content can also be consumed in our ArcGIS Runtime application. So applications built using the ArcGIS Runtime SDK could consume I3S content. And version, I think 100.1, I suppose, just got released. And in fact, you can go to the iOS store, download a sample application, and be able to see ArcGIS Runtime application directly consuming scene layers. So it's just a little bit overview of the products that we have and offer that allow you to generate content and also consume. But obviously, as Chris has shown, it's not limited to only Esri products. You can generate I3S, as most of our partners are doing currently, the Vricons, the Bentleys, and the Pix4Ds, or also consume it directly in a third-party application. Now let's talk about I3S. What is it? What is it really? What is I3S? Well, I3S supports storage and transmission of very large data consisting of millions of discrete 3D objects with attributes as well as integrated meshes. This may cover, thousands of square miles, or could be small site scale data. But the premise with I3S was that we designed I3S. It was a multi-team effort from our R&D lab in Zurich, our R&D labs in Beijing, as well as Redlands here. It was a multi-team effort to design from the ground up a cloud, web, and mobile-friendly system that depends on JSON and REST and modern web standards to stream 3D content. I3S was designed to support 3D geospatial content, paying attention to the various coordinate systems most of our users are already accustomed to. So I3S from the get-go had the requirement to support both projected coordinate systems and geographic coordinate systems, as well as the vertical coordinate systems that come with it. So if your data is an orthometric or ellipsoidal, it should be able to be supported and visualized in the different applications that we have or anybody might have. So just have to do the prerequisite definition. What is an I3S dataset? Then an I3S dataset, referred to as a scene layer, is a container for arbitrarily large amounts of heterogeneously distributed 3D geographic data. Note just the emphasis on arbitrarily large amounts and heterogeneously distributed, in that the content could cover vast amounts of geographic area, or also could be heterogeneous in type, points and meshes and integrated meshes are all supported within the system. Chris mentioned this already. So I3S is going through the OGC standardization process, and Esri supports OGC, and we hope to become an OGC community standard, and that would obviously increase the adoption of an I3S layer. Scene layer packages are, so as part of the I3S definition, the standard includes specification for scene layer package. Scene layer package is a single file that packages the complete node tree structure, as well as any resources that are associated with it, and supports direct access to this archive for the individual nodes and resources within it. And this is a key point, that an SLPK actually allows you to directly access it for rendering purposes and also for transmission publishing purposes, in that the same content that you use to publish as a service can also be read for a direct read format. And this has been very invaluable, as always Chris points out, that you can take hundreds and hundreds of gigabytes of large data and be able to drop it in a freely available application like ArcGIS Earth and be able to visualize immediately. And we can show that with some of the demos that we have here. So all that has been defined within the I3S standard. Both the I3S and SLPK are released under Creative Commons and is available on GitHub, Esri/I3S spec. I wanted to talk a little bit about some of the design principles that we had when we were designing 3D, when we were designing a 3D GIS visualization format like I3S. There were a few points that we wanted to address from the get-go. Of course, if you are designing a web streaming format, it needs to be web-friendly, and choice of modern web standards currently is JSON, and we stuck with JSON. But we didn't sacrifice performance. So JSON coupled with typed arrays for binary content for the mesh data and attribute data that accompanies an I3S layer was chosen, keeping the web friendliness, but also not sacrificing any performance. Mobile friendliness, that is, as in mobile systems, as you all know, bandwidth is a big question. Oftentimes you might have varying levels of bandwidth depending on where you're at. And an I3S layer that works in a mobile system needed to account for that. Extensibility is another area. Currently, I3S defines 4 types of layers. As Chris mentioned earlier, I3S employs this layer type and profile definition within the specification itself. But the system is extendable in that in the future we can add more types of layers, or anybody can actually extend the system because it's an open specification and adapt it to one's requirements. Declarative. I always say the best documentation for I3S layer is the I3S layer itself. The 3D scene layer JSON within an I3S layer actually have all the required documentation and specification for that layer to be consumed for a machine and also for human readable. It's a JSON. So this declarative aspect of I3S was key in that you don't need to have implicit knowledge in consuming or understanding this layer. That the layer definition itself is the documentation per se, that it will declare what is contained within that layer itself. And there are other points that we need to hit. Scalability is big. I3S intrinsically supports level of detail. Level of detail is built within the standard and within the specification itself, and often all of our applications that we have take advantage of that. Most of the users that actually work with this also wanted to be able to protect this, as evidenced by its implementation in the ArcGIS platform. You can secure either with named users or secure passwords an I3S layer such that ensuring that content is protected. And of course, obviously, it's an open standard that has been shared. Now let's just talk a little bit about the different layer types and profiles within I3S. And a demo would be much more telling, but I'll just briefly describe the different layer types that we have. So there are 4 layer types that are distinctly defined within the I3S definition or standard. 3D objects, integrated meshes, points, and point clouds. The first 2 are very much related in that the axis pattern, traversal pattern, and even the bounding volume hierarchy is very much similar within the first 2 layer types. So we kind of group those into a profile, mesh pyramids profile. Mesh pyramids also kind of resonates with a lot of people in that image pyramids is kind of similar architecture what people have for image. This is for mesh and image as well. So that type of layer, 3D objects integrated mesh, has been defined as mesh pyramids. As mesh pyramids profile. Points and point clouds are distinct enough in the aspects of traversal and generation. They warrant their own profiles. So we have profiles for points and point clouds as well. So the first layer type, 3D objects, what is it? And typically, this are examples of this layer type include building exteriors, landmark features, all those things that you would see within the scene application that you can select and view and identify. Typically, this type of data are derived from GIS sources or GIS data, as well as 3D models, as well as from 3D models from various formats. Now, the ArcGIS platform kind of allows you to import different formats, Collada, 3D Studio Max, OpenFlight, etc., into a feature class and be able to publish it as an I3S layer or a scene layer. But we have data, we have many partners that also allow you to actually import this type of 3D models and directly publish it as or generate as a scene layer. So 3D objects is the first layer type within I3S. Next up is integrated mesh. Integrated mesh, this is a mesh surface representing the skin of the Earth. It includes the vegetation, buildings, and roads, everything that you would see within a scene. This type of data set is typically derived from satellite imagery, aerial or drone imagery. Hence, our product Drone to Map is actually one product that allows you to extract meshes out of such imageries, or via dense matching photogrammetry processes, or it can also be calculated. So second layer type supported with an I3S is integrated mesh. Third one is points. Points are your canonical examples of points of interest, hospitals, schools, trees, and whatnot. But with an interesting twist with them that they could be actually also symbolized or instanced with a 3D model or geometry that you could be able to actually symbolize your whole scene. So points serve for that purpose as POIs as well as they could be represented via instanced 3D models. And then lastly, the one that has been introduced last was point cloud. This is typical examples include LiDAR data sets, both airborne or terrestrial or mobile LiDAR data sets could be sources for point cloud layers within I3S. Let's switch to Sean so that we can see a few of these examples actually in play.
Which one?
What? Three?
Okay. So thank you very much, Tam. So going through the examples that Tam discussed, we went from 3D objects, mesh, points, and point clouds. So we'll give you an example of some of the larger area coverages that we have for meshes. So this is some mesh data for Rio in Brazil. This is provided by Vricon. So you can see the multi-level of detail being brought in as you zoom in, and the changes that occur as you zoom across the screen. We also have, so this is at a large scale, so that will cover, as Chris said, 10,000 square kilometer tiles. We also have one of our other partners, the Bentley Context Capture. They do city scale models. So this is the city of Orlando. And this is also at multi-scale and also improves in resolution as you zoom around and zoom in. And this gives you, so it gives you all the buildings, all the terrain, and also all of the trees and other objects that are captured by the photogrammetric process. And then finally, we have the Pix4D generated drone to map data. So if you have a set of drones, this is was created in about 20 minutes from a 20-minute flight with 53 photographs this is in Rancho Cucamonga, and it you have the ability to extract out most all of the detail and all the geometry that is in the scene as well. So these are just examples of the mesh creation in I3S format. So moving on from there, we can not only take just a single layer, but we can actually combine many of these layers together. So this is a set of data which is for the New York area. It was collected post-Sandy by the USGS 2014. And this is point cloud data, 3D object data, and point data for a tree survey that was done on Roosevelt Island. So we have over 6 billion points for this particular set of data. And we then also have for the city itself, we have over 1 million buildings. So these are 1 million 3D objects. And in each of these objects, they actually have all of the attribution that would be relevant to that particular model. So so not only is the structure being being created with levels of detail, but you also have all of the attribution that comes with those features that you output. So you have buildings are being symbolized by their height, and then we can also look at the actual. These are point features, which have been symbolized using the online symbols, which allow you to generate a tree version of these points. So these are not actual tree models, they're actually points which have been symbolized based on their attribution. And then the actual point cloud itself. So this permits you to actually render the points, and then those points can be consumed by, as Chris said, by Pro or other applications, and then used in editing applications as well.
And right now you're streaming that from online, right?
Yes, so this is all being streamed directly from online. So with all of these combined, different sets of layers are all available in the online environment. Then we also have, so while with the 3D objects, we can render textured cities, or we can also render it without any textures, but we can actually render it based on the actual attribution. So this is looking at walk times, different walk times for different parts of San Francisco. And you have the ability through the JSON API to actually change those renderings on the fly. And it gives you the opportunity to mash up and create a whole series of different outputs for your clients or for your own use. So as Tam said, we have this also a set of information with regards to those layers that are available and information available on those in our online environment. And we have a set of example 3D scene layers. So if you're interested, you can, all you have to do is go look for the 3D scene layer group in ArcGIS Online. And all of those layers and all of the examples that I've shown here are available there for you to review and look at as well. So I'll hand it back to, yep.
Quick comment. In fact, there are already over 10,000 scene layers in ArcGIS Online, some public, some not, some behind organizations. So there's been pretty good adoption already. 10,000 scene layers and I think 5,000 scene layer packages. So, and about 25, actually I think it might have been up to 30,000 web scenes created. So we are seeing some good start to adoption there. Go ahead.
Thanks, Chris. Okay, thanks, Sean. So we did see a few examples of the different I3S layer types supported within the Index 3D Scene Layer standard or specification. Now let's talk a little bit about how is data organized within the I3S standard. Well, I3S organizes information using hierarchical node-based spatial indexing structure in which each of the nodes' payload contain features associated with attribute, geometry, or textures. So this is the essence of the I3S data structure, is that there's a node-based spatial indexing that gets created for any given input data. Looking at this diagram that we have on the screen and kind of blowing one of the nodes out, let's just look at the content of a node. So the physical organization of information within the node is as following. There is the node index document, which is this lightweight resource that describes the topology of the node within the tree and includes reference to other sub-resources. These resources are the shared resource document, which is a descriptor for material and image resources. So the shared resources within the node tells you where or what resources for material and image you have within that particular node. Second is, maybe I should highlight it, the feature data. So the feature data resource is a sub-resource that contains the identifiers of the set of features within the node. It stores the geometry and attributes for all of the features in the node by value or by reference as a sub-resource. And then next, we have the geometry data. The geometry data is the binary data that actually describes or defines the geometry of that node. Texture data and attribute data are also included as a reference within the node index document itself. So basically, when you look at a given node within the I3S structure, all of the resources that are referenced or all of the sub-resources that are referenced within the node may be available depending on the node structure. So for example, a single layer may contain texture data, untextured data, might have attributes or may not have attributes. So all that will not be an issue within a single I3S layer or could be accommodated within a single I3S layer because the data organization is per node and each node could have, may or may not have different sub-resources. So I3S promotes the concept of discrete levels of detail. So in the earlier premise or the principles when we set out to designing I3S, as I said, is level of detail is key or innate within the I3S structure. And I3S promotes this concept of discrete level of details within multiple discrete representation of features and nodes where a node where a more detailed representation of a node and its feature could be fully replaced by a coarser representation of node or a higher representation of the node depending on the level of detail that you are within the tree or within the tree hierarchy. Now, there is an example LOD selection metrics, one example LOD selection metrics that is employed to actually, so how does a client application select the appropriate node? Well, this is based, one criteria is for this, the LOD selection criteria is the maximum screen size. So the maximum screen size for a node defines that the maximum size the node may occupy on the screen before it must be replaced by a more detailed node. So typically an application actually gets access to this node resource document that I showed earlier and is able to define or is able to determine which level of detail it needs to request from the service or from the scene layer package before it does that request. So this really optimizes the data access pattern that you never ever get to request data until the point that you need to see it or render it. And this is huge. This has been great optimization within the I3S structure that a client application will only request for resources that it needs to visualize at the right level of detail. And information for that could be a prior requested without actually requesting the heavy duty resources, the geometry, the texture, the feature data. All those resources are occupy, the content size of these resources are usually bigger, so you never need to request this content until you are actually ready to render it. And this has been the differentiating factor with I3S as opposed to traditional access of data that you wouldn't know that you have this big data until you actually requested it and got it and are trying to render it on the screen. Continuing this consumption pattern, I3S exposes a couple of ways to consume an I3S layer or scene layer. First is via RESTful interface or services. An I3S node and its payloads can reside on a server, and it could be returned via RESTful interface, like we have done again with ArcGIS platform that exposes the scene layer. The scene layer then exposes the nodes and its associated resources, the geometry attribute, and textures as a web addressable resource. So that's one pattern of accessing it. But I3S also exposes the same content in a file structure within the SLPK that also translates to the same way that you'd address it or request it through the web. Doing that actually allowed the same pattern, the same access pattern, whether you're consuming it from a service or whether you're consuming it locally from a disk, is the same implementation that you need to have. So this is also very helpful, especially in environments where some of our clients may not be able to access web resources. This has been a great way of achieving the same performance and functionality. But it's not a closed system. It's very flexible and extendable, and we can mention a few of them. For example, depending on the layer type, we allow different bounding volume hierarchy to define this replacement, this maximum screen threshold. For example, what I mentioned, one is routinely employed by mesh pyramid layer types. 3D objects and integrated mesh typically employ that. But that's not the only one. That's not the only one. Similarly here, as far as the bounding volume, some of the layer types, points, 3D objects, and integrated mesh expose their bounding volume as minimum bounding sphere, whereas others like point cloud expose as oriented bounding box. So this flexibility within the system is very helpful, especially for different layer types, new layer types, or a third party that wants to introduce new layer type would become very useful. Storage. The node structure may be stored in this expanded format, or easy to navigate, easy to visualize with the complete metadata information about the node's position, bounding volume hierarchy, and topology stored as a file, as an individual resource. So each node that you see on a screen, or each node that you see addressable via URL, is stored as a file, say within the scene layer package, or it could be fixed in that we could employ optimization to store it in this paged, to store it to be more amenable for this paged access pattern. Yet another flexibility within the system is you can have either embedded geometry or binary geometry. So the geometry could be referenced as a binary source, or could be embedded within the JSON resource itself. And I mentioned the LOD selection criteria. Different LOD selection criteria are available depending on the layer type: maximum screen threshold, screen space relative, distance range, effective density are all options available within the specification. Indexing is, so there are two key aspects within the I3S layer structure that are key for scalability. First one is indexing, and the next one is level of detail. So scalability could be achieved by employing these two factors, indexing and LOD management. Now, I3S does not dictate or does not impose any specific indexing schema. You can use R trees, quad trees, oak trees, whatever may please the data really could be employed. Because as a consumer of this resource, your responsibility is not to be able to actually understand and use this, but just to obey what is defined in the node index structure. So that kind of disentangles, oh, is it regularly subdivided data or not? No, it could be anything, as long as it's described within the I3S data, within the node structure. That's what the client would retrieve and traverse. So different indexing schema are appropriate for different data types. Quad trees are particularly good for regularly graded data. Sparse oak trees could be very efficient for point cloud and dense data structures. And but the key with all of them is that data should be balanced across the nodes, or we should strive to achieve like kind of near constant data volume per node, because the application that would be requesting or retrieving these nodes would be able to not need to second case the content of a node, that the same kind of pattern would apply for one node will apply for everything else. Wanted to quickly show what are the steps of the I3S content creation when we employ Esri software, or when we do it internally, let's say. Well, the first thing is, so the green boxes that you see on the screen define the input feature data. And this input feature data is read and clustered into chunky enough nodes. So one thing that you really want to do is that you want to organize your node content in such a way that some features might be big. They might have millions of, in fact, sometimes we've seen millions of vertices, and some features might be very small. But I3S data structure allows you to actually cluster those small pieces of features that you have into a bigger node, and then also subdivide bigger features so that they are all amenable for this constant load across the nodes. So green boxes represent the features, the input features, and they are then clustered into this chunking of node. The blue circles define the nodes. Once the leaf node creation is done, bounding volume calculation is also done, and this screen error estimation. That's the value. The maximum screen threshold is one example that I mentioned earlier. Once that calculation is done, really after that you can complete populating the interior nodes with lower levels of details. So the interior nodes, the ones that you see with the hyphens, define interior node structure, where a lower level of detail is representing the features that you see in green at the bottom. So this is one way that we're able to achieve scalability, where interior nodes will be populated with alternate representation. So a client application will only need to display those nodes at that level of detail and never have to worry about or request the higher level LOD nodes. We employ this capacity-driven texture and geometry aggregation and reduction or decimation. Aggregation in that we collect, features that are too small into a bigger node, and then decimation to reduce a particular feature if it is too big to be visualized or handled. Yeah, you can take a look at the slides. Another key level of or key to scalability, again, I kind of hit it actually in the previous slide, is level of detail. There are two modes of level of detail. Node switching LOD. Node switching is basically a given node or the contents of a feature within a given node will be displayed on the screen, and if a higher or lower level of detail is required, that node must be replaced. So it's a full representational pyramid where each node represents the features that it collects into one piece of geometry. But then at the next level, higher or lower, you need to replace that node with its parent or children nodes. And this capacity-driven reduction of geometry and texture actually helps to achieve that. By keeping a constant volume data load across each node, we're then able to swap out, basically replace any given node with its parent or children, depending on the level of detail. Sure, we're a small group, so we can entertain a quick question. Yeah.
Is it immutable? Are you truly replacing the node, or are you?
Well, so different clients can employ different optimization that, for example, so here's the question. Is the node replacement immutable? Are you completely discarding and replacing the node, or are you just temporarily just removing it from the scene graph, let's say? Both approaches could work. Now, some rich client application, desktop client application, actually capture a representation of that or cache that locally, so that if you traverse up and down the tree, you are zooming in, zooming out, let's say, and you displayed a particular node. Most of the applications don't ask back the service to give them back the same content because you already have it, you already visited. You can also keep it in memory depending on your memory budget, so that if you are loading nodes that are at a certain level and you just turn it around, you might want to keep it in memory so that the next time you turn around, it immediately shows. So both approaches could work depending on where you are, depending on how vastly different, so that will work. This breadth first kind of approach will work when you are zooming in and zooming out. But if you are zooming or navigating at a constant LOD level, for example, that might not work because you are visiting so many different nodes across the layer structure. So just moving up on the slides. Quickly, let's just take a look at the scene layer package standard. So the representation that you see here is really what a scene layer package is. There is a scene layer package is actually very interesting because it's a very optimized archive container. So all the resources are compressed within the archive itself. But the compression is only applicable for the individual resource. So the archive itself is not compressed. There's just a zip64 with a store option. But the individual resources within it are compressed. So why is this important is that you never have to actually extract the content from this huge zip archives that, SLPKs that, data partners create and have, if you're extracting like 150 gigabytes of archive, it's going to take a long time, just even extracting it. So
it takes about 20 to 25 seconds to
just load it.
to load 120 gigabyte
right.
SLPK and allow you to start navigating in and out on it. So that wouldn't be possible if the archive itself was compressed at the top level.
Right. So that's a key feature of a scene layer package, that it doesn't sacrifice compression or compactness within the scene layer package, but it also allows you to directly access it within the scene layer package itself, such as what Earth does, ArcGIS Pro does, or any other client that consumes scene layer package directly. This just shows, the slide shows just the file layout, what it looks like in file folder structure. All resources, the hyphenated node names that you see here are the individual nodes, and each individual nodes can contain attributes, features, geometries, or shared resource or textures. Go ahead, yes.
You may have already answered this, and I missed it. If you have these folders with all that information, how do you get from that to the SLPK?
Okay, so question is, just to repeat the question. If you have all this resource that you have shown in the screen, like this folder structure, how do you get from there to a scene layer package, right?
You literally, I do this actually a bit. So I'll get a SLPK from a partner, like Bricon. They've just got a standard pipeline for it. And let's say they haven't updated their pipeline to put a pretty name in the SLPK. I will open 7-zip. I will use it to extract the SLPK. I'll manually edit the JSON, and then I'll use 7-zip and re-zip the whole thing at storage compression.
Yeah.
And it's trivial. It's like I said, we're the human parsers because it's so accessible.
Yeah. So any archiving, actually, you can use any archiving software, 7-zip, WinZip, RAR, whatever it is, to create an archive with store, no compression, but just store option. And then literally just copy the content and put it in there, and name it .slpk, and that's pretty much it. As long as you have the right structure, as long as it's got the the node structure defined properly, and the 3D scene layer, which actually is the entry point. This one right here, 3D scene layer.json references the content. We're running a little bit late on time, but we have yet one more demo at the end, but I wanted just quickly to go through just a quick overview of what the geometry buffer what the geometry buffer is in I3S. So the content that you just see in dotted lines are optional, but the content that you see in bold or in the green are required. So the geometry description has a header. The header just tells you how many, what the vertex count for that geometry is, and optionally the face count and feature count if defined in the 3D scene layer JSON. Then followed by the vertex attribute, the positions, X, Y, Z, as 3 floats would be there, and then UV, the texture coordinates, if the content has texture, would be there. Followed by normals and color, any color data that geometry has. So this is the definition of the geometry layout. Similarly, the attribute data is also stored aligned with the geometry. So each node resource has an attribute data aligned with the geometry layout of the node. More information is on the I3S spec, where we have examples and demos showing actually, or example data that you can download. So let me switch it back to Sean. We are at the 2:30 mark, so maybe we can do like a 5-minute or 7-minute demo, and then we can open it up for questions.
Okay.
All right, thanks.
Am I on?
Yeah.
Yes. Okay. So going back to, so this is the ArcGIS Pro desktop application. So here we have New York, so same set of data I showed to you earlier. And we have so in this case, we have the actual local file geodatabase so for the buildings. And turning it on, you can see it's not rendering quite quickly, but it's getting there. We also have the actual SLPK, so this is a local data set. And as Tam said, it loads the whole set as one piece. And when you zoom in, it is loading the different nodes. And in Pro, you can see it loads them quite quickly. And the same way with the point clouds. In this case, with point clouds, you have the, so this is the last data set format. So it's loading, trying to load all of the tiles into it. In the SLPK format, it'll load.
Unload the last first.
Yeah, it's
unloading the last. Yeah.
So it now has to load all of the point clouds in one set, and these point clouds are been indexed and will switch out the different levels of detail as you zoom in. And as you know, as I said earlier, all of the information is captured within these SLPKs. So, and as Tam said, all of the attribute information. So if you have, in this case, if you have different classifications, unique values, or RGB, you can render those data by that, and also you can modulate using the intensity for that set of data for the point clouds. And you can also increase the number of actual points that are rendered. So the base, depending on the client that you are using, it can run quite quickly in both a lightweight web client, and also you can add, you can run it quite efficiently and do editing as well in the desktop client. So,
yeah.
Right?
So this is night and day, actually. The same kind of layers earlier he showed consuming being streamed as a web service, but it's exactly the same identical resource. Here he was showing it as a scene layer package being directly consumed from the SLPK itself. Again, the only difference between the previous one and this one is just latency, when it comes from the web and comes locally. But other than that, the optimization for both the selection criteria is exactly the same. And this, I think, has been very beneficial for a lot of users that want to just use it locally also. So we have about maybe 10 minutes or so before we conclude. So since it's a smaller group, we can just open it up, questions or any comments that you might have, and go from there.
Go ahead, in the back.
So one of your slides indicated the extensibility.
Yes.
Can you give us an example of what you mean by that?
Sure. So the question was, one of your slides, in fact, let me switch back to here. 4, I guess, yeah. And just bring up the I3S. So, am I projected? Sorry, not yet. I have to end the presentation, I suppose. Yeah. Okay. Just before going to your question, there was one slide or one demo that I wanted to show. This is an example of an SLPK generated by a partner. I think is this context capture? Aerometrics.
Using context capture.
Okay, Aerometrics using context capture generated this. And look at the fidelity or the quality of this cars and trees. It's really amazing. And they were able to actually capture it into a scene layer package, generate it, share it as a service, or load it locally in ArcGIS Earth like I'm doing right now. So I wanted just to highlight that the quality could be, or the type of data sets that are captured as an I3S or scene layer could be thematic, as Sean was showing us, point cloud data, or the building data classified by their usage, or they could be very realistic models representing the real world with the trees, cars, and everything else captured as a mesh, and really performing very adequately. Now going back to your question, you mentioned you were asking like what are the areas of extensibility that is allowed within I3S itself. Well, I3S actually, when we started, when we first released it, had 3D objects and integrated mesh really defined and available. Those two layer types, points and point cloud were added later on. That's part of the extensibility. Now, if we were to add, let's just throw out another one, BIM. The I3S structure actually allows you to do that you can define a new layer type and specify it within the I3S umbrella specification.
Conceivably, we've had a variety of things asked for, such as GLTF as a payload format. That's something we haven't looked at yet, but it's conceivable that we could actually, somebody could modify the spec to add in GLTF as a payload format. And for those who don't know what GLTF is, it is a 3D model format that's been adopted by the Kronos group, who is kind of the non-geospatial standards, one of the non-geospatial industry standards groups. And GLTF is an optimized format for 3D content parsed through WebGL.
Right.
So that's an area where we've had questions about it, but we haven't done it yet. It's conceivable somebody could. Additional texture formats. Yeah. One of the things that Vricon has said is they're really excited about the share-alike attribution with attribution licensing that we're planning on for the OGC version of the spec, because what they want to do is actually expand the spec to accommodate up to 16 bands of up to 16 channels in imagery. They process satellite imagery. They don't just need RGB. They actually want to add multispectral bands, and so the really exciting stuff. Lots of stuff like that. So those are all areas that we can envision the spec being expanded to include, and I'm sure there's lots of stuff that we haven't even thought of.
As
What you meant by extensible is that it's more of a spec extensible rather than user extensible.
Yeah, like users can do. So this is a data-centric spec. I mean, users can do whatever they want with it. We have people who have who've combined I3S scene layers in our WebGL viewer with the 3JS renderer and created crazy measurement tools on top of I3S. That's not really part of I3S. I3S is one of the content types being consumed in there. But from the user side, I mean, Esri has a ton of libraries, SDKs, and it's an open spec, so anybody can create whatever functionality they want on top of it.
Yeah, I agree.
There was another question right here.
I had a question regarding the distribution of the data.
Mm-hmm.
Very good for visualization, for example. But if somebody wants to visualize the attributes that they using facade,
Sure.
So,
what is the capability of
so the question is, what is the capability of using attribution within the layers?
Sure.
Sean actually demoed one
Yeah, you can bring
version
it
of that already, but go ahead. Here.
To the thematic. Yeah. Sorry. You are number 3? Oh.
Yep, that's right. Okay, so in the thematic side of it, so this is what I demoed earlier, where I'm actually rendering from the actual the changes that are in the actual attributes. So this is reading off the attribute table, changing the colors based on those attributes, and then actually theming, and you can actually generate the differences when you using those attributes, either by texture or also by actually querying as well. So.
Back up. I'm sorry?
For example, individual building facades, if I have different attributes for each building facade.
And individual building facades, that?
You mean texture or what?
Let's say I have some information.
Yeah, that's exactly. So what Sean was showing was that each building has attributes stored with it, and this could be usage, data type, whatever you might have as part of the attribute of each feature.
Each side
Oh,
of the building.
okay. So okay, I got
So
it.
in
Okay.
in the
Okay.
in the 3D object layer type that we're showing, each object is a single feature, and you don't have interaction with those individual component geometries.
So,
But under this, so we also can consume, so I work extensively with the City GML standard, so The City GML standards defines that each feature you have, for each building, you have a floor, walls, and
Face.
roof, and faces. And then if you go deeper in, it goes further into the interiors. So we can consume that also and output that as a I3S scene layer package or scene layer service. And all of that information is maintained within the actual feature itself. These examples we're showing are just individual buildings, so they can be broken out into separate faces.
That will be my next question that I already answered. Regarding the interoperability with the city GML,
Mm-hmm.
it's not clear there, I guess.
So,
Can someone convert the data from
okay,
city GML or other?
good. Repeat the question, yeah.
Yeah, so the question was, is if somebody has a set of City GML data, is it possible to convert it to I3S, the scene layers, and what tools to use for that? So right now we have a set of tools built on top of Safe Software's interoperability tool, and that will permit you to bring your City GML data in and all of the attribute information in it into a feature class, and then be able to directly export into a scene layer package as well.
You know, I do want to caution though. So the current 3D object cooker that is in Pro, yeah, thank you. The current 3D object layer cooker that's in Pro, it kind of stops aggregating things at the scale of approximately a building. So if you try to take a BIM model or a highly dense City GML LOD4 model and dataset and run it through, you can visualize it and you can see it, and they'll have attributes and you can interact with the data, but the performance won't be great because essentially the nodes at that lowest level get huge. And we are doing a lot of work right now to come up with some alternative profiles and layer types to try to deal with that kind of data. So that's one place where we're working on optimizing I3S production. From what we're doing today, I fully expect somebody else might come up with a way to do similar things with a different pattern inside I3S.
Yeah, related to somebody else might be able. The I3S specification itself actually captures information per vertex. So in the geometry payload of the data, there is some segmentation information, but that segmentation information right now is per feature because that's what typically people have. But if you really wanted to generate, each facades of the building or different sections of that, it's up to you. The specification does not have any limitation. It's just that input tools that we currently use are based on a feature, and each feature is defined as one object. So, yeah, that's something to consider.
Yeah, we've already done some experiments where we can decimate down to the micro dust level and actually just zoom in and out all the way down and then back out to the city scale, and it works very performantly, but that's not implemented in our cooker yet. Yes, sir.
With the REST structure, how smart does the server need to be, and does the client have all the information to construct the full path to the individual
Okay.
file?
So the questions with the REST API, does the client have all the information it needs to construct the full path to each of the nodes?
Yes, it does. So the node index document actually always have by a relative URL to all the resources. So the client application, all the client application is doing is it captures or retrieves this node resource document, and from that node resource document, it reads all the resources of that node, geometry, texture, attribute, or anything else. So the way that is done is that if you were to cache that, so there is a secondary caching of that resource, for example, and we typically do that. That resource will stay static. It is not going to change. So any secondary or tertiary caching that happens behind the scene would also benefit in that the resource that a client application requests kind of stays static for that resource for that node. In fact, in our implementation, the REST implementation in ArcGIS, these node resources have an expiry date of 24 hours or a very long time, so that the back-end or front-end infrastructure that caches this doesn't discard it. So you could actually benefit from that.
So we're actually at time. Is there one more question anybody has? Go ahead, Elliot.
Just curious about the timescales for, you talk about coping with BIM data and looking at what methods of dealing with that. Have you got, or is it's into the long term?
No, we've got some active both collaborations and research R&D efforts going on right now, and I actually hope to start to see some fruit from it this year. BIM is a huge multi-domain, multi-technology problem set. So what we'll probably be looking at first is the architectural side. Roads and highways will be another bit of complexity, and then pipes and culverts and stuff will be a whole other bit of complexity. So it's a pressing, huge problem set with a ginormous opportunity. And on a separate topic related to that, we actually have had Esri UK built an integration on the web side between Autodesk 360 and ArcGIS Online, so that you can at least open up the Autodesk 360 interface inside a web scene. That's a very lightweight integration. It's not streaming thousands of BIMs into GIS, but we have that requirement and we're working on it.
Right.
Good question. Anything else? I'm going to have to run soon.
Yeah,
here,
we have to run to a session. But
thank you guys all
thank you
for
very much.
hanging out, and we hope it was informative for you.
Yeah.